Greetings everyone. I'm Nishkal Rao from IISA Pune, India, joined here by my collaborators Apratim Ganguly, Anupreeta More, and Anuj Mishra. I'm incredibly grateful for this opportunity provided by the collaboration to share some of these fascinating insights that we have developed through our project on the comprehensive analysis of time domain overlapping gravitational wave transients. The focus of this presentation is to discuss some of these interesting results regarding, say, whether a lensing signal can actually mimic an overlapping transient. This insight is very crucial for ensuring accurate parameter estimation in gravitational wave astronomy, especially with the advent of the upcoming detectors. So, today, I will introduce some of these overlapping gravitational wave transients, describe some of the lensing effects that we consider, specifically type 2 strong lensing and microlensing, present our data analysis techniques, including parameter estimation and fitting factor methods, discuss our results in depth, and say touch upon some future work. So, as binary black hole mergers become more and more routine with the current detection runs of LIGO, we need to further characterize scenarios where two nearly simultaneous compact binary coalescence occur. Although this is extremely rare for current detectors, estimates predict that overlaps will become extensive as sensitivity increases. This results in a time frequency complicated overlap, which has been very well explored in several recent works, some of which I've cited in the references. So, on the left of the slide, you can see a scenario where a very loud signal dominates the entire overlapping strain represented by the dotted signals, whereas on the right is a situation where these two signals are of comparable overlap and a comparable strength, and this leads to much more complex overlap, leading to some beating patterns that we observe here. So, the overlapping pattern that we discussed kind of closely resembles the single image lensing analysis frequently studied by you, the experts. In our analysis, we consider two primarily single image lensing analysis. These regimes type 2 strong lensing. This is characterized by introducing a phase shift, a constant half integer multiple of pi, that modifies the time domain structure of the waveform in certain aspects of the parameter space. Further, microlensing. In this regime, the lens is less massive, and we observe some frequency dependent amplifications. Here, wave optics effects become significant, leading to complex patterns in both time and frequency domains. These lensing effects have the potential to mimic the beating patterns seen in overlapping signals, which is why understanding these degeneracies are so essential. So here, on the top, we recover an overlapping strain with the type 2 lens template, and on the bottom, you see the waveform recovered using a microlens template. So here you can see that the recoveries reproduce the amplitude modulations and the phase shifts that are closely expected from overlapping signals. This similarity in signal characterizes some degeneracies, some overlapping space, making it challenging to distinguish whether this complicated waveform that we get comes from two overlapping events, say singles A and singles B, or a single lensing event of one signal. So, motivated by some past studies on recovering individual signals from overlapping parameter estimations, we began by analyzing a set of varying three critical parameters: the chirp mass ratio between the two signals, the SNR ratio, and the difference in coalescence times. So, we recover the overlapping signals with, say, standard unlensed analysis done in LIGO, and further on with lensing templates with strong and microlensing. By exploring these spaces through parameter estimation and fitting factor optimizations for a fixed grid of points, we expand our study to the population consists of a lot of signals, right? So that we can study the specific parameter spaces, the pinpointing the regimes where overlapping signals strongly mimic lensing effects. Thereby, we can better understand how each factor contributes to the observed degeneracies. So the analysis techniques, we perform typical Bayesian inference and fitting factor maximization, similar to LIGO analysis. And then the key parameter that we compare is the base factor difference for model comparison. We maximize the fitting factor over the primary components of chirp mass, symmetric mass ratio, and the lens parameters. So this is computationally less expensive, and we extend it to our population study so that we can understand in which conditions and lensing template might erroneously mimic an overlapping signal. So, We found that overlapping signals introduce significant biases in parameter estimation, as observed in previous studies. For example, the chirp mass often shows bimodalities in the recovered space. Additionally, the louder signal typically dominates the recovery. So, if one signal has much SNR, its characteristics can overshadow the weaker signal, leading to biased estimates. This is often very well understood and is intuitive given we have seen the plots earlier. This finding motivates us to search for alternate waveform structures that our overlapping signal might mimic. At the population level, our fitting factor results confirm the individual case analysis. So, as the time of coalescence increases between the two signals, recovery improves and biases are reduced. As earlier, for minimal time differences, the biases are significant, and this highlights the challenges posed. So, now we explore the core of our study, that is the type 2 lens template to recover overlapping signals. Our analysis shows that if we force the template to include the characteristic Morse phase shift of type 2 lens, we see slight improvement in base factor over unlensed given by these differences. So on the right side, where we allow the mouse phase to vary rather than fixing it, the lensing characterization improves. This suggests that a single strongly lensed template in specific regimes can effectively mimic the combined waveform of two overlapping events. The median Moss index that we recovered is kind of close to the type 2 value, indicating higher support for such recoveries. Further, at the population level, the data favors the type 2 lensing interpretation for signals with minimal difference in coalescence time. This suggests that a single strongly lensed template in specific regimes can effectively mimic. And further, as overlap decreases, the evidence for lensing drops and recovery reverts to what is expected for an unlensed signal. In most regions, the evidence support for type 2 lens recovery, however, remains minimal, as seen by a typically flat prior. Further, the interesting scenario of microlensing case. So when we use microlensing templates to recover overlapping signals, they provide more substantial support in cases of extreme overlap. Additionally, the recovered lens parameters, the redshifted lens mass and impact parameter, specifically vary systematically with differences in coalescence time, indicating a stronger case for microlensing at higher overlaps. A very interesting plot is presented here from the cumulative posteriors for cases with extreme overlap given by the blue region, which is with smaller coalescence time differences, the microlens recovery actually favors large lens masses, as seen here, and lower impact parameters, which is the clustering of these higher recovered lens masses and lower impact parameters actually strengthens the idea that overlapping signals can closely mimic the effects of microlensing. This result is very critical because it indicates that if we do not adequately account for strongly overlapped signals, we may risk misinterpreting them as microlensed evidence. So, at the population level, further, the microlens fitting factor results support our individual case findings. When the overlap is very strong, microlens templates yield high fitting factors, and we see striking differences in the SNRs and chirp masses, which can give higher support for microlensing. In conclusion, our study confirms earlier research that overlapping gravitational wave signals pose a challenge for parameter estimation, mainly due to degeneracies with lensing effects. On recovery with single unlensed signals, we obtain high-V biases at stronger overlap, suggesting the need to further study these effects. We find that these overlaps can mimic type 2 strong lensing and microlensing in specific regimes, which may lead to misinterpretation if not carefully addressed. Further, we address the issue of the recovery in microlensing signals and have set up some runs fixing the Fourier convention in the study. Moving forward, we plan to, and we have some results to explore the parallel study of eccentric templates as a potential method to understand some more of these degeneracies, thereby improving our detection and characterization of overlapping events. These are some of our references that we have used, and thank you all for listening. I'm extremely delighted to share these results, which have taken incredible efforts over 2 years. We began this project to analyze both modeled and unmodeled searches in order to cohesively identify overlap signals. And as literature proceeded, we further examined whether lensing and eccentric effects can mimic overlapping strains. I'm genuinely grateful for the guidance and support from Apratim and Anupreeta throughout this project, and I thank the LVK collaboration for hosting me. I would be very happy to take some questions or hear some feedback. Thank you.